Great. So it's a great pleasure to welcome Benjamin Dupont, who's coming from the Université de Lyon, who will be telling us about computing bases in two categories. Take it away.
Well, thank you very much. So first of all, I would like to thank all the organizers of this seminar to give me the opportunity to give this talk here. It's a wonderful experience but I can do it online now these days. So today I'm going to talk about how to compute bases in linear two categories using rewriting theory. Okay. The outline of the talk will be as follows. So in the first part, I will introduce and motivate the use of rewriting theory in order to compute bases, and in particular, in order to prove some non-degeneracy proofs and some explicit categorification results. In the second part of the talk, I will explain how the categorical framework to rewrite in linear two categories, and I will explain how to obtain the two fundamental properties of computation that are termination and confluence. And I will illustrate this construction on the example of the KLR, Khovanov, Lauda, Rouquier algebras. And then in the last part of the talk, I will explain the extension of these methods for pivotal linear two categories with the use of rewriting modulo, the isotopy axiom of the structure. So first of all, let me begin. So the main question beyond the talk can be stated like this. So when presenting a structure, like let's say an algebra on a higher category by generators and relation, how to know how large the algebra is? And that is to say, how large it is, that is, can we know that it is not vanishing to zero, or that we have sufficiently relations to have the structure and prove what we would like to want? And in general, to know which size has an algebra, there are two things that we want to prove. We want to prove that we can have a basis. And in general, given a set of relations, it is possible to find a spanning set of the algebra, because let's say, depending on the relations we have, we can always try to guess which will be the basis elements. But once we have some candidate for the basis, it's hard to prove the linear independence of these elements. And indeed, in general, we try to prove the linear independence by proving that, by defining a polynomial action of our algebra on some polynomial ring and trying to prove that the candidate basis acts by linear independent operators. But this can be quite difficult to achieve in general. So the idea is to try to find tools, find computational tools adapted to computation of such linear bases of presentation of algebra and categories. And as I said in the introduction, the main objective beyond this is that oftentimes when we define a categorification of a structure, we define a higher category, let's say a two category, and we want to find some basis of each of the morphism spaces to prove that the category constructed really is a categorification. And in particular, this is the case for the Khovanov, Lauda, Rouquier categorification of quantum groups, on which the question of the non-degeneracy has been an important question. And today I will present some stuff based on rewriting theory to compute this basis. So let me state what is rewriting theory. First of all, in an algebraic context, rewriting consists in taking algebraic structure presented by generators and relation, and to fix an orientation of the relations to try and deduce some properties of the structure from this orientation. In particular, rewriting theory has been developed in many contexts in linear algebra. For instance, there were some works for associative algebras with Bergman and Bogut. There are some works for commutative algebras with the Gröbner basis and the Bohrberger algorithm. There are some works on Lie algebras with Kirchhoff, and then on non-commutative algebras with Mora and some other names that I didn't quote here. And more recently, there have been some work that have been developed for operas with works of Dotsenko and Koroshkin, and for higher algebra and categories with some works from Giro, Hofbeck, and Malbos with the introduction of the structure of polygraph, which we will talk a lot in this talk. Before going into details, let me give you an example how rewriting theory can be useful to tackle these questions. So take an associative algebra A and consider that A is presented by generators X and Y and submitted to relation X squared equals XY. That is to say, A is the quotient of the free K vector space on the free monoid over X modulo the ideal generated by this relation. And so if we want to study this algebra from a rewriting theoretic point of view, we don't need to have this as an equality, but we need to fix an orientation of this rule. And let us choose to orient these rules from X squared to XY. Once this is done, let us consider this word, for instance, this yxxxy. On this word, one might notice that there are two possibilities to reduce this word using our rules. So first of all, we can apply our rule on the first two x. And I draw this as a double arrow as a hint of what I will talk about later. So here we can reduce xx into xy and we obtain the word yxyxy. But we can also apply the same relation of the rightmost xx to obtain the reduction to xyx xyy, like this. And this is what we will call the scheme of reduction of the same element by two different rewriting steps is what we will call in the sequel a local branching. Now on this scheme, one might notice that the y, the leftmost y and the rightmost y actually is not useful at all in the computation. We are never using, we are never reducing this y and this y. And at least we can remove both these y's and have the same reduction scheme. And now we have this reduction scheme on a word that is minimal. Minimal in the sense that there is no letter in xxx that is not reduced by a word. And this is what we will call a critical branching or an ambiguity, if you may have heard about this from the works of Bergman. And now one can check that the word that we have on the left, xyx, does not contain xx anymore. So this one is irreducible, and we say that it is a normal form for our set of reductions. On the other hand, the second word, xxy, can still be reduced. Indeed, I start with xx, so I can apply my rule, and I can reduce to xyy. And again, I am a normal form. So here, I have the scheme of reductions of the word xxx, and I cannot apply more rewriting rules. So on this example, sorry, one might notice many things. First of all, the rewriting system that we gave with the arrow oriented in red like this is terminating. That is, there will never be any infinite rewriting sequence with respect to this set of rules. And the reason why is, for instance, you can use a Deglex order stating that x is greater than y. Deglex order means that I first choose to a word is greater than another one if it's larger, I mean, if its length is bigger. And then it's just a lexicographic order on a fixed order on the alphabet. So if x is fixed to be greater than y, then x squared is greater than xy. And this is an argument to say that this rewriting system is terminating. Once we have a terminating rewriting system, we know that we can always pick a word and apply as many reductions on this word as we want. And finally, we will reach some either monomial or linear combination of monomials that are irreducible. And that is sufficient to say that the set of irreducible monomials, or monomials in normal form, will be a spanning set of the algebra. However, we can see in this example that it is not sufficient to have a basis because in this case, they are not linearly independent. Indeed, xyx and xyy are two normal form monomials which represent the word xxx, and they are different. So there are two different linear combinations of monomials in normal form. And the reason why this holds is that we are missing some properties of computation, which is confluence. And confluence states that whenever you have two different paths to reduce a same element, so here xxx, you need to be able to find some paths to converge towards the same element. And this is the property. And now, and I will tell more details about this later, but now that we have, if we have termination and confluence combined, then it will be sufficient to say that the monomial in normal form will form a basis. And let me begin with a fundamental result of algebraic rewriting, which is a criterion to obtain confluence. And this criterion says that if we have a linear rewriting system, which is terminating, then confluence, to check confluence, it is equivalent to check confluence of these minimal overlappings that we call critical branching. So if we know that we are terminating, checking the confluence amounts to a finite checking of all these minimal overlappings that we, in general, are able to do. And we have this result that we can call under this form the Bergman diamond lemma, saying that if we have a rewriting system on which the relations are compatible with a monomial order, as it was the case for the previous one, so if we can orient the rules with respect to a monomial order, then the irreducible monomial will form a basis of the algebra if and only if every critical branching of the presentation is confluent. And this is an expression of a famous result, the Bergman diamond lemma. Let me just state one stuff that we will use in the sequel, that this condition that to be oriented with respect to a monomial order can be weakened in some way and replaced by we can have a terminating rewriting system. And this is what happened in the context of polygraphs, and I will talk about this in the section 2. But before going into section 2, let me give an example of what one can prove using this kind of arguments. And this, for instance, is the Poincaré-Birkhoff theorem. So consider a Lie algebra L and consider a totally well-ordered basis X of L. Then one might know that the universal enveloping algebra of L admits a basis, which are the words x1 power alpha 1, xk power alpha k, where x1 is smaller than x2, smaller than xk. And how to prove this? Well, first of all, one might fix a presentation of the universal enveloping algebra. And for instance, consider a presentation on the generators. And these are the relations that we have to impose. And now, if we want to study this from a rewriting point of view, we have to fix an orientation from this relation. So let's say that here y is greater than x. It is natural to orient this relation in this way. So to have yx reduces to xy, and plus this bracket, because the bracket being a word in the monomials, being an element of the Lie algebra, I mean, it will decompose in the basis, and then it is a sum of words of length 1. So by a Deglex order on this would be a terminating rewriting system. So yeah, if we fix a Deglex order on x1 smaller than x2 smaller than xk, this choice of orientation gives a terminating rewriting system. And now that we know we are terminating the Bergman, we just have to check that the critical branchings are confluent. And critical branchings are minimal overlapping of two reductions. So here we can express their forms. Indeed, if we look at these relations, they are on the form zyx for x smaller than y smaller than z. These are the cases when I can have an overlap of two relations. And one might show that their confluence is actually equivalent to the Jacobi identity of the Lie algebra. Indeed, consider zyx. You can reduce it using the first reduction on zy into this sum. On this element, you can reduce the zx part because z is greater than x, and you obtain this word. And on this element, you can reduce the yx because y is greater than x, and you obtain this sum containing xyz as a leader term. And on the other side, you can also choose to reduce yx first, and then you obtain this sum and keep going. So you have zx, you can reduce here, you obtain this element. And here you have zy that you can reduce and you obtain this sum. And actually, so here it does not seem confluent, but you can try and make the difference of these two elements. And the x, y, z terms will cancel. And you might see that this being 0 is actually just equivalent really to the Jacobi identity. And so actually, we just prove that we have under the assumption of the Jacobi identity, we have a rewriting system that is terminating and confluent. And as a consequence, the normal form monomials, for which one can easily check that these are these kind of words, x1 alpha 1, xk alpha k, form a basis of this universal enveloping Lie algebra. And so this is the first proof of the Poincaré-Birkhoff theorem. So that is an example of of how rewriting can be used to achieve some linear basis. But as I said, what I want, the algebra case is quite well known, and what we are interested in is more the context of the presentation of linear two categories. Actually, what I was interested in first is the whole family of diagrammatic algebras that arise in categorical representation theory, let's say. And so my objective is to study some kind of diagrammatic presentations. So before explaining the link between diagrammatic presentation and categories, let me give an example. So for instance, if we consider K to be a field, we have such an example given by the Nieleke algebra of degree n, which is the K algebra presented by some family of generators x, y, and tau I, like this, and this big set of relations. And you might know that this algebra can naturally be equipped with a diagrammatic interpretation with the generators xi being polynomial or represented by this diagram consisting in n vertical strands with a dot on the ith strand. And the tau I being a symmetric group diagram can be represented by this diagram, so containing a crossing between I and I plus 1 strand. And modulo all this local relation. And if we look at local relation, if we decide to that multiplication of the algebraic terms is equivalent to vertical juxtaposition of diagrams, we can also equip these relations with a diagrammatic interpretation. So for instance, this is this one. So xi, xj is the word xi that we read from the bottom, xj here, and xj, xi is this one, xj here and xi here. And we can do this process for all the relations. So here, tau I xj is this relation equals xj tau I, and tau I tau j equals tau j tau I is this relation. So these three relations, are just expressing commutative distant relations between the generators dot and crossing. And then we can do the same for the other relations. So here we have tau I squared equals 0. So this is this relation. We have what we call the Coxeter, the Yang-Baxter relation, tau I plus 1, tau I equals tau I plus 1, tau I plus 1, that we can present like this. And finally, we have the relation, the commutation relation between the dots and crossing that creates some extra terms that we can represent like this. So this is an example of what we call a diagrammatic algebra, but actually, one might see that studying this algebra, so the algebra Nieleke of degree n, is quite complicated in the sense that it contains many relations and that there is a more economic way to study these algebras, which is to encode them inside a two category that contain all these algebras in its morphism space. And that's what I will explain now. So yeah. Before explaining how to construct these two categories, let me recall the link between two categories and diagrammatics. So let me recall that a two-cell of a K-linear monoidal category or K-linear two category can be represented using a diagram that we call a string diagram. So this representation is Poincaré dual of the globular presentation in the sense that zero-dimensional objects become regions of the plane, so two-dimensional objects. One-dimensional objects, arrows here, still are one-dimensional objects, and two-dimensional objects become some boxes or dots or whatever we want. And note that in this talk, we will decide to read string diagrams from the right to left and from the bottom to top, which is a bit tricky, but that's the convention we choose to use. And now one knows that in the two categories, there are two different ways to compose morphisms. So there is a star zero composition given by gluing two cells horizontally, and star one composition given by gluing two cells vertically. And this has also an interpretation in terms of string diagram. So star zero composition amounts to take two string diagrams and putting them next to each other in this way. And star one composition, provided that the one target of the two cell F and the one source of the two cell G match, we can vertically compose F and G, and this is given by that diagram. And once we have this composition, we have to impose this relation, which is a structural relation of a two category, which is the exchange relation, and which states that given any two diagram, there is a way to have this diagram at different heights always. So it's like some distant commutation relation that we will use, and that is a structural relation of a two category. And now let me just explain. So we had the Nieleke algebra, if you remember the relation, and we try to define a two category that encode this Nieleke algebra. So first of all, here the set of zero cells. Here we see that we have no regions labeling the plane, so it will be just a singleton. The set of one cells will be the number of strands on the diagram, so it will be just the natural integers. And as the set of two cells, we would like to impose, as the set of two cells, we have to construct the diagrams. So the diagrams here, it will be the K-linear, we are in a linear setting, so it will be K-linear combinations of diagrams that one can build using some generating pieces that are crossings and dots. And on these diagrams, one wants to impose some relation. And we should have to impose all the relations of the Nieleke algebra. But if you remember, the first relations were just some distant isotopy relation. And in that context, that doesn't have to be imposed because there are structural relations that come from the exchange law. So finally, we just have to impose all the remaining relations, and we have to impose them in a local context because we are in a two category and we have some pasting on the left and right, and we could recover all these relations. And actually, when we define this two category this way, it is the two category that encodes the Nieleke algebras because if we look at the endomorphism space of n in these two category, it is isomorphic to the Nieleke algebra of degree n. And so actually, instead of studying all the Nieleke algebras from a rewriting point of view, we will just try to study these two category that only contains 4 relations. So which means there are only 4 relations to orient. Okay, so now that was the motivation. And now we want to describe what is rewriting on string diagrams in two categories. But first of all, the natural question that arises, what is a presentation of a two category? And this is where the objects called polygraphs arise. So polygraphs were objects that were introduced by Buroni and Street independently in the 70s. And they were introduced to as generating system of higher categories. And actually, so whenever we have a structure, a categorical structure, we will try to present it by a polygraph. So first of all, the first example is the algebra case. And let me explain how to present an algebra by a polygraph. So associative algebras over a field may be seen as categories with 1, 0 cell that are enriched over the monoidal category of K vector spaces. And in such a construction, so these are one categorical objects that we will present by 2-dimensional polygraphs. And they are presented by linear 2 polygraphs that are triples P0, P1 that are made of the following pieces. So always when we consider a polygraph, the first P0, P1 will be an oriented graph with a set P0 and the set of edges P1 with source and target maps on P0. And in that case, because we have only 1, 0 cell in this categorical interpretation, always P0 will be a singleton, and P1 will always be made of the generating 1 cell of the algebra. Then the next step to present the algebra is to define what is, once we have the generators, is to define the monomials. So to do so in this context, we will consider the free one category, P1 star, on this data. And free one category means I take all the paths that I can make in my directed graph. So here, since everything has source and target this bullet, I can take any composition and it just amounts to multiply the generators, and these contain monomials. For instance, x squared y is an element of P1 star. And then we have to linearize in some way. So once we have the free one category, we will take the free one algebra generated by this graph, which is defined by taking if I take two generators, here I should have two words in the generator, so two monomials. I will take the free algebra P1L between x and y, sorry, will be the free K vector space generated by P1 star and also with source x and target y. So I take all the monomials. The one cells in P1L should be all the linear combination of monomials, so the free K vector space on the free one category. That's how I should define it, because here it's well defined if I have many 0 cells. So yeah, the most important part is I take the free one algebra, so I take the free K vector space on the free one category, sorry. And then I need to give a sense to relation of the algebra. And this is given once we consider rewriting with a cellular extension. And cellular extension is just the data of a set equipped with two maps, S1 and T1, that go from this set P2 to the free algebra and satisfying globular conditions like this. And this globular condition just state that the elements of P2 have really a globular shape of two cells that we expect to be two cells in two categories in some way. And the source and target maps consist in fixing an orientation for the relation of the presentation. So here, once we take the cellular extension P2, we just take the relations of the algebra and we fix the orientation, and this gives the source and this gives the target. let me give an example. So if we consider the algebra that we already see presented by generators x, y, and relations x squared equals xy, then we can present it by a linear two-poly graph with 1, 0 cell. The generating one cell of the generators x and y, and the cellular extension is given by x squared and xy, these two cells with source x squared and target xy. And this is the general framework how we can generate a structure using a polygraph. And this is what I want to do, but for a linear two category now. And so as a hint, here it was two-dimensional objects. For a linear two category, it will be three-dimensional objects. So let me define what is what we call a linear 3-2 polygraph. So 3-2 polygraph, 3 means for the dimension, which is a three-dimensional objects, and 2 means for the dimension on which we have linearity. So here we will have linearity from dimension 2 on 2 cells and 3 cells, and not before. So this is the common notation. So before I should have said 2, 1, but it's more, yeah, for some reason it's more common to say 2. And a linear 3-2 polygraph, sorry, is a quadruple this time, made of P0, P1, P2, P3, when P0, P1 is still an oriented graph, on which we still construct the 3-1 category. But this time it's a bit different because P0 is not necessarily a singleton. And once we have the 3-1 category as a basis, we will consider a cellular extension, P2 of P1 star, that consists in generating 2 cells. So P2, in the case of string diagrams, the elements of P2 will correspond to the generating diagrammatic pieces. And I will illustrate this on the Nileker example afterwards. And then once we have P2, we will consider the 3-2 category on P0, P1, P2, and this contains all the star 0 and star 1 composition of generating 2 cells. So this encodes the way to build all the diagrams from our generators. So we have our generators, and we star 1 and star 0 and star 1, which means horizontally and vertically, compose them to obtain some new diagrams. And these new diagrams lives in the 3-2 category P2 star. And then similarly, we linearize. Oh, sorry, that's a typo again here. So we linearize. So if we take 2 1 cells U and V, then the set of 2 cells between U and V in this linear 2 category should be the K vector space generated by P2 star between U and V. Sorry, there's a typo again here. So we have the diagrams with source U and target V in P2 star, and we take the free linear 2 category on this, so which means we take K linear combination of such diagrams. And on this, so this is the setting where we want to impose some relation. And to impose some relation, we will once again consider a cellular extension P3 of this free linear 2 category. And this cellular extension contains a fixed orientation for the relations. So this might be a bit unclear so far, but let me illustrate this with an example. So for the Nileker 2 category that I defined a bit earlier, so to define this, we will again have 1, 0 cell because we have no regions labeling the plane. And if you remember, I said that the 1 cells will be in correspondence with the natural integers corresponding to the number of strands. So here to generate all these 1 cells, we need to have only 1 as a generator. And the 3-1 category will be this set of integers n, because 1 might compose 1 with itself as many times as you want, and you obtain n like this if you compose n times. And then the generating diagrammatic pieces that we want is we only need to have a crossing operator and the dot operator. So the crossing goes from 2 to 2, so 2 strands to 2 strands, and the dot goes from 1 to 1. And then we need to define the cellular extension P3, and P3, it amounts to define an orientation for the relations. And here we had this family of 4 relations before, and we decide to orient them in this way. So the double crossing will reduce to 0. We have this choice of orientation for the Yang-Baxter equation, and we have this choice of orientation for the dot relations. And to sum up really quickly this construction, so first of all, we always take the construction of a polygraph in any dimension. We can say we first take an oriented graph P0, P1, on which we construct the free one category. We take a cellular extension P2, which are the generating diagrams. We construct the free linear 2 category on this data, and then we take a cellular extension that fixes an orientation for the relation. And actually, if you choose a different orientation for the relations of the category, it defines another cellular extension and thus another linear free-2 polygraph to study. And I will not talk about that at all today, but one can rise in dimensions and construct the linear free category generated by this data. And this structure is where the rewriting steps, so our arrows allowing to rewrite a diagram into another one will live. So I just say this for this reason, but I won't talk about this construction at all. Okay, so now we have the generating structure to talk about presentation of category, but now we want to discuss about how to rewrite in this data. So first of all, to do so, we need to define a few key concepts. So the first one is the notion of monomial, and a monomial of a linear free-2 polygraph is a 2-cell in the free-2 category P2 star. So it corresponds to the idea that we have, that is just a diagram and no linear parts. It's not a polynomial. Then we need to define, in order yeah, I should say a bit more here. So we have our set of generating relations, but as you have seen in the context of the algebra, we allow to apply our relations with some context, that is with some words on the left and on the right. And here is the same. The relations that we gave as a generating relation, we will allow them to be applied with some diagrams around. And this, to define what is a proper reduction, we need to define what is a context. And a context of a 2 category is a pair SC, where S is a one sphere of C. One sphere means a pair of parallel 1 cells of the category. So it's 1 cell with the same 0 source and 0 target. And C is a 2-cell in the 2 category C of S, where C of S is the 2 category formally extended by a 2-cell with source and target this 1 sphere, such that this 1 sphere appears exactly once. So this might be unclear, so let me rephrase. And explicitly, S will be a whole, what we consider to be a whole, and the context will be a 2-cell in which we have 1 whole and that contain exactly once this whole. So for instance, here we have this sphere in red. This is a 1 sphere. And we can star 0 and star 1 compose whatever monomials we want around. And here, this is a whole, and this is a context of this whole. And in terms of string diagram, it can be represented like this. So I have these diagrams, and in the middle of my diagram, I have a piece where some stuff is where I plugged the formal cell S, and this is a whole that I want to fill. And this is a definition of the context, but I can also define a context in a linear setting. And to do so, actually, I will keep the same definition, but I will just add to have some linear parts, that is multiplication by a scalar and addition of a polynomial on the right. So a polynomial, a linear context, sorry, is such a context where I multiply by a scalar lambda, which I can do because I'm a linear 2 category, and I add a linear polynomial h on the right. So it's just the same thing, but I have a monomial in which I have a whole, and on the right I have a polynomial. And this is a linear context. And this allows me to define what is a rewriting step. So rewriting step of a linear free-2 polygraph is a free cell of the form. So I take alpha in P3, and I will allow to reduce S2 of alpha in a context. That is, I have my diagram S2 of alpha, and I add some context around. So I add some diagrams on the left, on the right, on top, and on bottom. And I rewrite into T2 of alpha with the same context, that is with the same diagrams around. And this is exactly what we have in mind when we say that we apply relation locally. That is to say, we keep the same data around the application of the rewrite of this rule. But this is not enough. There is a condition that we have to impose, that is that the monomial here, the monomial on which we apply the source, so the monomial that contains S2 of alpha, cannot appear in the polynomial part H of the context. So I apply my rule on monomial that cannot appear in the polynomial context. And why? The reason is the following. So let's assume that I'm not adding this condition, then I will have a clear termination problem for this reason, because let's say if I have a free cell from u to v, then I would expect in my linear setting to have a free cell from minus u to minus v. And then I would expect to have a free cell from v, which is equal to v to u plus v minus u. And if I rewrite this minus u into minus v, then I would have a free cell from v to u. So I start with a free cell from u to v, and I have a free cell from v to u. And this, I cannot do it. So I have to impose this condition here that the monomial on which I apply my rewriting step cannot appear in the polynomial context. And here I apply my rewriting step on u, but u already appears in the polynomial u plus v, so this is not allowed. And this is not a rewriting step. And one technical condition that I have to impose once for all is that we always consider some linear polygraph that satisfied some left monomiality property. And left monomial mean that for every rule alpha in P3, so every generating rule, I want S2 of alpha to be a monomial. And this is not a big assumption to make, because if you imagine that I want to rewrite a polynomial into some other polynomial, then I can always fix a monomial in this polynomial and reduce into the polynomial that I want minus all the terms that I removed on this polynomial. So this, if I can always find a linear 3-2 polygraph that will present the same linear 2 category and that is left monomial. That's how I should say. Now that this is defined, we can talk about rewriting. So we have defined the rewriting objects and rewriting steps. So we can talk about rewriting properties. So I already mentioned most of them, so I will go quite quickly on this. So first property is termination. So there is no infinite rewriting sequence with respect to the polygraph. So rewriting sequence here means concatenation of rewriting steps. So these rules in context. Then we define a branching. A branching is a pair alpha beta of rewriting paths, which has the same two source. And a branching is local if alpha and beta are rewriting steps, that is of length 1. So if you want to have a picture in mind, you can have a look at what is drawn below. And then we said that confluence. So confluence is a property that one might give for a branching. So we said that a branching alpha beta is confluent if it can be closed by rewriting paths alpha prime and beta prime like this. So this is the property that we are trying to reach. And finally, we say that the polygraph is confluent if any of its branching is confluent. If you can solve any branching using your rules. And one of the big theorems in rewriting theory, so this is a very general theorem, but it works independently of the algebraic context. That is, whenever you have a rewriting system, you will know that under termination assumption, confluence and local confluence are the same. So this is already a good refinement, because if you want to check confluence, it is sufficient to check local confluence, that is confluence on rewritings on length 1 only. And then we have, as I already mentioned a bit before, another better criteria, which is given on critical branching. So critical branching of a linear 3-2 polygraph is a local branching alpha beta, which comes from an overlapping of between two rules. So yeah, I didn't talk too much about the classification of all branching, but the ones that we are interested in are already the ones on which there is an overlapping of two relations, because the other ones can be considered but are always confluent. And such a branching is a minimal for the order on branching for the given by fg is smaller than f, but in a context. So let me explain with an example. So if you look at the example of the Nieleke algebra and you take, for instance, this diagram, well, you might see that you might try to see on which parts of the diagram you can apply some rewriting rules. And here, on the second, third, and fourth crossing, starting from top, you have a Young-Baxter relation that you can apply, and same on the fourth, fifth, and sixth crossing. So here you can see that you have only two places to apply a relation, and actually the crossing that is on top, the first one, is never appears in any of these reductions. So this part that I put in red is useless actually in this scheme of reduction, and it's as in the case of the algebra, we can remove it. And now we can see that on this part, we have a source of a free cell alpha, and on this part, we have a source of a free cell beta, and alpha beta here is a critical branching, and it's something that we will have to prove confluent at some point. So before talking about how to prove termination, let me just say that critical branchings, so we know them in the case of algebra, it's just a pattern matching algorithm to find all the critical branchings on words, on monomials. And in the case of linear two categories, it's a bit more complicated to describe, but we once again have a concrete classification of all critical branching, and they are classified into 3 families. So the first one of the ones that we imagine at first sight are the regular critical branchings. So regular consists in, I have a diagram on which I can apply a rule beta on f and h here on the top left, alpha, sorry, and I can apply a rule beta on h and g on the bottom right. And this reduction overlap on the central part h. This is a regular branching. And the example to have in mind in the case of the Nieleke category is the one that I just gave. So this application of 2 Young-Baxter on top of each other, they overlap on the central crossing here. This is a regular critical branching. Then we have inclusion critical branching. So inclusion critical branching are given by, I have a big diagram on which I can apply a rule directly. And I also have a subpart of this diagram on which I can apply another rule beta. And this, we have no example in the case of the Nieleke category. And in general, it's rare to see some presentation with such examples, because when you have such a presentation with inclusion branchings, you can always modify the presentation to avoid this kind of branching. So I won't enter into details for this here, but we can always find a presentation when we have no such branching. And finally, what is a bit different from the algebra case is that we have what we call indexed critical branching. And index are defined as follows. So let's assume that here on f and h, on this part of the diagram, I have a source of a rule alpha. And on h and g, a bit like in the case of the regular one, I have the source of a rule beta. But on the right, or on the left, or on both sides, I have an identity part, like a vertical part with no generator, on which I could come and plug anything that I want. Here is some diagram K. And for any K that I could plug, I would have to check. It would give you another critical branching to consider. And for instance, the example to have in mind here, so in the case of the Nieleke, we have index critical branching. And here I have always my pattern of application of Young-Baxter on top of itself. And on the right, on this identity part, I can come and plug a dot or n dots. And if I plug n dots, this gives me a branching that is different from the one that is above. And that is some case that I have to consider. Hopefully, I don't have to consider such index branching for all the diagrams K that I can plug here. And actually, Giro and Malbos proved that it is sufficient to check for the K that are in normal form, which is already a bit better. But in that case, it also gives us some work because we have to check for the dots. The dots are in normal form. And we have to check for the crossings with n dots on the bottom left, which are also in normal form. So it gives more work to do to check this critical branching in that context. Okay, so this critical branching lemma is just to say, it's a recall. Terminating linear free-two polygraph is locally confluent even only if it's critical branching or confluent. So this is okay. And finally, so we are interested in computing linear basis. So the result is the following due to Alom in 2016. So if P is a left monomial and convergent linear free-two polygraph, presenting a linear two category C, then for any parallel one cells P and Q of C, the set of monomials in normal form with respect to P between P and Q is the linear basis of the home set of two cells between P and Q. So I take all the diagrams that have source and target Q, and I reduce and I consider the monomials in normal form in this, and they form a linear basis of this set of two cells. So now we have seen that actually when we have a terminating linear polygraph, it's quite easy to check the combination of both properties because checking the confluence amounts to just checking the confluence of this minimal overlapping. So it might require some work, but it is in some way quite automatic. It's just a check of calculation. But actually, the difficult part is to be able to prove termination in that context. And let me explain a bit why. So in general, you have a rewriting system, let's say a linear rewriting system, and you want to prove termination. So what you want to do is to define well-founded total orders such that, well, it's in the other direction. You want that the source of your rule is strictly greater, sorry, it's a typo here, is strictly greater than any monomial in the target. So you want that the source of your rules are bigger than the target of your rules. And you want that if you have an element that is smaller than another one, therefore for any context, you keep the same order. It's to say if you have u less than v, then c of u is less than c of v for any context. Indeed, if you're able to define such an order, it guarantees termination. Why? Because assume you have an infinite sequence of rewriting steps like this. But by definition, in the case of two categories and in the case of algebras, these rewriting steps come from application of rules, so generating rules in a context. So u1 reduces into u2 is just a context of u'1 reduces into a context in u'2, with u'1, u'2 being just a generating cell. So if we know that u'2 is smaller than u'1 and we have stability by context, this would yield an infinite strictly decreasing sequence for our order, but if it is well-founded, this is impossible. So this is the what we want to construct such orders in general. And I already mentioned this, but in the case of the algebra, this order often amounts to checking that our relations are oriented with respect to a monomial order. And a monomial order is a total order such that if I have u less than v, then I have w u w prime less than w v w primes for any monomials. And for example, degree lexicographic order that I talk in the introduction, or such monomial order. So if I know that my relation can be oriented in a compatible way with a degree lexicographic order, then I have a terminating rewriting system. And for instance, this is another example. So I gave one in the introduction, but another linear two-poly graph for an algebra that we know to be terminating because rules are oriented with a Deglex order on x greater than y greater than z. However, this is the case for algebra, but for the case of two categories, to define such an order is way more difficult because we do not only have one operation, one multiplication operation, we have two operations, *0 and *1. And for example, if you want to take the algebra A, which is the algebra of the symmetric group S3, and you consider this relation here, so the Young-Baster relation. So in the case of the algebra, it would just amount to define a relation between two generators S and T with STS equals TST. So if we take S to be this generator crossing in vertical strand and T to be vertical strand and crossing, this is exactly this relation. And to define an order in this algebra would amount to count the number of S, for instance, because we know if we have STS reduced to TST, then we have more S on the left than on the right. But this works only if we have three strands, and this doesn't work in the two-category case, so in the two-category Nieleke, because we can plug diagrams on the left and on the right, and counting this number of generators become quite tricky. So this argument does not hold anymore. So we need to find some other way to define such orders that are stable under contexts. And the correct setting to define this order is the one of derivations. So derivations were first introduced by Yves Guiraud in a paper of 2004, and then described in the categorical framework that we know now by Guiraud and Malbos in 2009. And that's what I will explain now. So first of all, let me explain the idea of the construction. So the idea is that any two cell will be seen as an electronical circuit whose electronical components will be given by the generators. Then each generator will receive a certain intensity of currents. So some will be ascending and some will be descending. And these currents will be calculated with some mappings X and Y that we define on generators and that we will extend functorially. Then, given the intensity of current that each generator receives, any two cell will produce some heat, and heat is calculated by the sum of heats produced by any of its components, of its generators, but depending on the intensity of current that they have received. So let's say if you have some current that come in on the bottom of the diagram, then the first generator will return some intensity, and the next one will produce different heat because it will receive different intensity. And these heats will be just formally calculated with these derivations d. I will explain more about that, and then we will compare two circuits this way. So if for any two circuits we give them the same intensity of current ascending and descending, then the two cell is greater than another one if it produces more heat. That is, the one two cell is smaller than the other one if the heat produced is smaller than the second one. Now let me make it more precise, but it requires some material. Yeah. So first of all, let me say sorry that yeah. So this is okay for if we have just some monomials, some circuits, but we can extend this construction to polynomials by setting that f is smaller than g if d of f is strictly smaller than d of h for any monomial h in G. And if we make this, if we define an order like this, one might see that we can only work with derivations on monomials. So we have to define the derivation framework on monomials of the linear two category. And to do so, I will define, I need to define some key notions. So as the time is already passing by, I don't know if I should define all of this or just go to the example.
Go to the example, please.
Okay. So first of all, I will define the category of context of the two category, which is a one category with zero cells or the two cells of the category. So here the objects are the two cells UV of my category. And the one cells from F to G will be the context such that G equals a context of F. So the arrows will have this form. I take a string diagram and I send it to a string diagram, which is F in a context. So I just make my string diagram bigger. And I say that a C module is a functor from the category of count to the category of abelian groups. And now what I will do is that I will, in the case of two categories, so following this idea of the heats and intensities, I will define some prototypical example of such modules. So first of all, let me consider O to be the two category with one zero cell. One cells are partially ordered sets, and two cells are monotone map.
Benjamin, can I go straight to the KLR algebra? We don't have very much time, so.
So what, sorry, you want me to?
Can you go straight to the example of the KLR algebra?
So I have some stuff to, so I let you check to compute the derivations, but yeah, I might go through the example. So the key is that this theorem, if we might find some two functors x and y that satisfy some inequalities on the source and target, and a derivation such that d of the source of alpha is strictly greater than d on the target of alpha, then it's enough to prove termination. And so yeah, I want to illustrate this on the example on the KLR algebra, because it's complicated and it requires this this technique of proving termination into further steps of derivations. But I will do it for the first part, which consists in the free two polygraphians here. And so I want to prove the term for this linear free two polygraph. And to do so, I will define my mappings y and x. So in many cases, we will consider the ascending currents, which are encoded in the functor y, to be trivial. So we will only be interested into descending currents. And we will take x of the generating one cell here to be the set n. And then so that we extend it to be x of 1 star 0, 1 to be n times n. And then we have to set values for x and d on the generators. So I didn't explain it really, I'm sorry, but it is enough to define this functor x and d and the derivations d on the generators. So here I consider this mapping. And then I have to check.
So can you explain this part more slowly? So what is actually happening? X is telling you, X of this generator is giving you a map from n cross n to n cross n.
Exactly. And d it gives me a map from n cross n to z, because d of 2 cell is a morphism from x of this times x of this to z by definition. And yeah, so but these are these assignments, and if you read before, you might know, you might see that it is the type that we want, and then we have to check the inequalities that we want. So first of all, x on the get. So here, if we compute x on this, by functoriality is just x on the crossing applied on m n plus 1, because m n plus 1 is x of the crossing, and this is n plus 1 n plus 1, and this is greater than 0, greater than nm also, which is x on the, here 0 is enough because a has target 0. And then we can also compute x for this. So x for the source of the Yang-Baxter is x of this on a k m plus 1. This is x of this on k n plus 1 n plus 1. And this is just k n plus 1 n plus 2. So this is just functorially, so it's not too complicated, and to check that we have this equals this. So this is correct for the assumption of the theorem. And then we define the mappings like this. So x of a crossing, so yeah, sorry, I recall that x of a crossing is this and d of the crossing is this. And now we can compute the derivation, which is the interesting process. So derivation on this, on nmk, you have to decompose this diagram into a context, into two different contexts. So this is just crossing strand, *1, this. So to compute this, y being trivial, the formula is like this. So you take d of the under part, and you take d of this part in the identity. I mean, in the identity, and you take d of the upper part applied to x of this on nmk. So the first part here, because I couldn't explain how the derivation behaves on context, but whenever you have a vertical strand, you might forget it. So here is just d on the crossing on mk.
Is it mk or nm?
Mk, because we read from right to left. So n correspond to the, it's a bit tricky, but n correspond to the first one, and then is d of the crossing on mk, plus d on this on nk m plus 1, because this is x of this. So by the assignment that we made, d of this on mk is k plus, and we can continue. So we take d of the downward part strand crossing on nk m plus 1, plus d of crossing and upper part on x of na of nk m plus 1, which is k n plus 1 m plus 1. And finally, we find that it's 2k plus m plus 1. And we can do the same for the other one. And for the other one, if we apply the same process, so we can derive the formula in one step, and we find m plus 2k. And so we see that on the source of the Yang-Baxter relation, we have strictly more heat than on the target of the relation. So it's sufficient to say that this rule terminates. And same for the other one, but the other one is more natural to consider for termination. And finally, this proves that the 3-2 polygraph of permutation is terminating. And I'm sorry, I wanted to talk about rewriting modulo, but I guess it was too long the beginning. So I will just finish with the example of the KLR algebras. So let me recall, I assume that most of you know about KLR algebras. So I will just fix that I take gamma to be the Dynkin diagram of a Kac-Moody algebra, G, with set of vertices I. And for assumption in the computation, I will assume that gamma is simply laced. And on this, I will define the KLR algebra R of mu, where mu is an element of the semi-group generated by the vertices of my graph. And the KLR algebra is an algebra generated by these generators that look like the Nieleke ones. So I have so here my strands are labeled by some colors of the Dynkin graph. And I have a dot generator and a crossing generator. And these are the relations that I have to impose to define a presentation of the KLR algebra encoded in a 2 category, as I've done in the Nieleke. That is, I might forget about the distant isotopy relation, the distant commutation of the generators. And I just consider the relations that I need to present define a free-two polygraph presenting a category encoding these algebras. And I decide to choose the orientation of this relation in this way. And I might prove, this is result that I get in 2019, that this linear free-two polygraph is convergent. So first, the proof of termination is using derivations into two steps. So I can define derivation x and functors as I've done for the polygraph of permutations, and I can do this independently of the color on the generators, and I can prove that this works well. So first, I can reduce termination to termination of the polygraph with only the dot relations, so the dot that go down on crossings. So I remove the double crossing cells and the Yang-Baxter cells using the same process that I just explained. And then I can reduce I can prove termination of the polygraph for the relation on the dot go down. And this is enough to prove termination. And finally, confluence is just an exclusive study of all critical branching. So I gave an example. So if I take this one, on the downward part, I can apply a double crossing relation, which gives me this element. And on the upper part, I can apply a Yang-Baxter relation. I am in the case of colors when I create a residue, an identity. So this gives me this diagram. And I can keep applying my relations. So here I can once again apply a Yang-Baxter relation on blue, red, red. And I get this element. And finally, once I'm here, I can only apply the relation that make the down go down on my crossing. So here, the first one go down directly because it's two different colors. And the second one does not goes down, but it's an Nieleke relation. It creates an extra term that will cancel this one. So finally, we will prove that it's confluent. And now that we know it's terminating and confluent, we might check for the monomials in normal form, and this will give a basis of the morphism space of the two categories. But in this way, we can recover basis for all the Kähler algebras. And I'm sorry, I don't have time to talk about that. Really sorry. But if you have some question, I would be really happy to answer.
Okay, let's thank Benjamin. All right, please ask your questions.
I know I've asked you this before, and I always forget, but if you try to do this with cyclotomic quotients, does something go wrong again? I forget.
So yeah, actually, that's a good question, because that's what I'm working on now with Gröbner.
Ah, okay.
Yeah, it's not properly for cyclotomic quotient, but we are trying to consider this kind of rewriting. But when you quotient by an ideal, saying, let's say, like you have the diagrams and the leftmost trend being red is killed, and or the leftmost trend with endos being killed. And yeah, actually, it's way more complicated to describe rewriting there. Because yeah, first of all, we cannot work really in the categorical context, because plugging something on the left would bother this condition.
It's not like a
yeah. So we have to work in the dimension of the algebras, so that's what we are doing. And we have to work in the dimension of the algebra, but modulo the distant isotopy relations in order to mimic what we are doing in the category.
But presumably that's not so hard. The hard part has to be the fact that it's not confluent unless you add a bunch more relations, right?
Yeah, so for cyclotomic quotients, we didn't try yet, but I assume this is the complicated part. And we are trying to go through this by computing some kind of DD enhancement of the cyclotomic Kähler, cyclotomic Nieleke and stuff. But this is also quite complicated to achieve.
Like there's that weird fact that killing two dots on the first strand also kills the first symmetric polynomial on two strands, and there's no way that that's going to be confluent unless you also include the elementary symmetric polynomial on two strands as a relation.
Yeah,
and so forth. Like there's all these relations that decrease in degree, and one obviously won't be implied by the other. So.
Can you flip through the remaining slides?
Yeah.
Can you show us the remaining slides?
Yeah, sorry. So this is explanation of pivotal categories. This is explaining the difficulties that we have. So,
talk about difficulty one.
Yeah, so first of all, when we have a pivotal category and we have some bubble slide relation, it's hopeless to try to find a terminating writing system that presents your structure, because by definition of the bubble endomorphisms and by axiom of exchange law, if you have a bubble state relation, you can take a bubble and make it come into a cap like this. But you can again apply bubble side relation to go it outside of the cap, and this by exchange relation it is equal to the first term. So anyway, you will have this rewriting cycle, and you cannot work with terminating rewriting systems anymore, but you have to work with quasi-terminating rewriting system, which are terminating but up to loops. And when we are terminating but only up to loops, it's a bit like the terminating case. I mean, we know how to handle this quite well for all the results, even for the basis results and stuff.
How do you handle, like, what do you need to show?
Sorry?
How do you handle it? I mean, there's obviously some condition that needs to be checked for something quasi-terminating. Or is there not?
That you just want to show that those terms show up infinite number of times, right, Ben?
Yeah, exactly. Yeah. So
Like,
in any infinite rewriting sequence, you have the same term infinite number of times, and you just pick one step. You just pick one representative, one quasi-normal form on which you just say, okay, now I have this element, and I fix my preferred element, and I stop here. So for each cycle, you fix a preferred element that is a quasi-normal form. And this is what we do when we compute the basis for KLR2 category, because we say, okay, so I choose the element on which the bubble is in the rightmost region. But the bubble could come back on the...
What if you have a cycle, but not in sort of normal forms? What if you have a cycle and things that can be reduced? Is that a new kind of ambiguity?
you would have a critical branching somewhere if they could be reduced.
Yeah.
So
Yeah, exactly.
you have a cycle, but there's branches coming out of the cycle.
It still counts as a critical
Give us some on further slides. Maybe you can go to the next slide.
But yeah, then I don't explain too much because I was expecting that I wouldn't have too much time to talk about modulo, but so yeah, for sure.
This is just, he's just showing that like he's breaking up, showing rewriting in terms of like rewriting modulo some previous steps. And so it allows him to break it into pieces where he can do like isotopies first.
Yeah, exactly.
Say,
so is there a good introductory reference which treats the 2D case, but in like more elementary examples, including isotopies? Like just not necessarily linear. So set theoretic is like just introductory reference which works out two-dimensional examples, including
in the case of rewriting modulo, you mean?
Just kind of basic reference which does this, well, not in this fancy settings, but in just more basic case with lots of examples and not linear. So what's the kind of first reference? What's the learning reference about the story?
Yeah, sorry. So if you want to see about just strictly rewriting a theory for two categories and not in a linear setting, I could refer to the Guiraud and Malbos paper of 2009.
Do they have
the modulo?
Do you have something which is kind of human readable, something with lots of examples?
Okay,
something
so
lots of examples worked out.
In the paper, they are doing the polygraph of permutation and also the polygraph of pairs, which is the first step of isotopies. Because it is the first step to prove that the rewriting system of isotopies is convergent. And as Aaron was saying, we are trying to split the termination and confluence proof in two steps. And first one is to prove that the system of isotopies is convergent, to then say, okay, once I get my quasi-normal form for my rewriting system, I take the normal form up to isotopy, and it's okay, I get to a fixed element. But rewriting modulo.
Also, which paper is that? I think Ben put a reference, but I mean, Ben put names, but do they have just one paper or many?
This is the 2009 paper.
Which one?
Where they do the symmetric group via derivations. Which paper is that?
This is the Guiraud Malbos 09, but it's not rewriting modulo, because rewriting modulo, it was part of what I've done in my thesis. So rewriting modulo did not exist in this context of polygraph. So my work was to say, okay, the KLR2 category is too complicated to handle if we do not take the isotopy in a different way. So I tried to find a context to study this two category, and it came out to be rewriting modulo these axioms. And it's exactly trying to split confluence and termination into two incremental steps.
So the case with isotopies is on in your paper. So people haven't, in your thesis, people haven't studied this before. When you have isotopies, when you don't have just things going up, but you can have U-turns. So that's on in your thesis.
Exactly, yeah.
Yeah, and before people only studied the case when things go up only, so to speak.
So when things go up, yeah, I can refer to the to this paper by Giro and Malbos. It's not isotopy, but it's where they introduce this derivation technique and they checked about confluence and also coherence in higher dimensions. So it's a good way to get used to rewriting techniques.
And so when things go up, are there examples beyond the symmetric group? Are there some kind of other interesting examples beyond the symmetric group?
What about the one about the Brouwer category? Isn't there the nice your
But Brouwer isn't what kind of involves
Allume? Doesn't he have some good examples?
Yeah, so this one is interesting because the affine Brouwer category, it was studied with a non-modulo setting in Alom's paper, and I also studied it with the modulo isotopy paper. So this paper is a series of two papers, and the first one is just the basis result, and the second one is the study of the KLR2 category. So maybe I can refer you to the first paper if you want to see introduction towards this technique of modulo. And also Alom's paper is also studying the Brouwer category, but without modulo and with these pivotal actions.
So this was your first paper.
Okay.
Yeah, I mean, it looks like a very powerful technique, so I'm just kind of curious to learn more about it.
Yes, so it's I think it's quite new, and clearly it's lacking some tools yet, like some need to implement like how to make sure that we have the complete list of critical branching, and then how to make sure that they are clearly confluent. It lacks some tool to prove confluence yet. So far it's a big work to first prove it's terminating and then try to find all the critical branching and compute them by hand. And I think if we are able to find some tools, some implementations of this, it would be a very powerful thing to.
So I wanted to add that back in the mid-90s, Greg Kupperberg has a paper, Spiders foreign to the algebras, where he did reductions to normal form for spiders, for spiders foreign to the algebras. But he had to check that overlaps resolve in a consistent way. And I think that's a special case. So it will be interesting to just rephrase Greg Kupperberg's work in this language, just to see a match. I think it's going to be much easier than the cases you're working with, than symmetric group or KLR, but just to see how the familiar language converts into your language.
Yeah, sure. Yeah, sure. To look at these examples for sure.
It's going to be kind of tricky though. If you want to, for webs, if you want a confluent presentation, you need some more relations than you think.
We did, sorry, because with Stefan Gosson, we checked a bit for webs, how to make it confluent. And yeah, we didn't go into full confluent presentation, but so I don't know what are the difficulties in that presentation yet.
Actually, that would be a really interesting problem because I know for like SLN webs, people are kind of interested in bases. They have this stuff, the
webs, you mean?
Yeah, I think for SLN, it's much harder. That's
right. So if they were able to produce a basis, that would be a good result.
But I mean, so I would check the work of Scott, right? Scott Morrison, I guess Sabin Kautis, and I think
Kautis, Kamens, or Morrison.
Joel Kamens. I forgot if it's 3 offers or 4. But so he have a full set of relations for SLN spider. But I don't know if they have a basis.
They don't. I have a basis of that category in my paper.
They have a basis.
They don't have a basis, but I have a basis of that category.
Have a basis.
In my light ladders paper. But again, the basis is complicated, which makes you think that if you're going to have a rewriting system where this kind of basis is...
maybe a basis can be restated using rewriting.
Right. So there's at least you're going to need some sort of Reidemeister 3 for rungs move as part of your relations, and it's basically Kautis, Kamens, and Morrison's relations, but I think souped up with a couple extra relations if you want it to be confluent. But it may be good.
So my other examples are other interesting set theoretical examples beyond examples like the symmetric group. So theoretically, when you don't have linear structure, you just have monoids, roughly speaking. Are there kind of consistent set of examples in 2D for this kind of things beyond obvious ones like symmetric group, template deep monoid, etc. When you don't have a linear structure?
Sorry, Michael, your question is just about like the rewriting.
Examples that you don't have linear structure and there's no addition in the background when it just sets and.
I think this is where the theory all came from with these guys like Ross Street and these Malthus, like they were doing.
But my question is, did they find lots of interesting examples beyond the ones that we know? We know symmetric group, we know Brouwer category, we know template deep monoid, just in the monoid case. Do they have examples beyond those that in the theoretical case? But I guess we can just check the papers. So it should.
Yeah.
I can tell you a good example, which is like the associated graded of the Categorification or Morrison-Webb's category. Can be done with just sets, not linear.
Oh, I see, and so it has it's consistent. So it's theoretic.
Yeah, I can show you. I'm writing a paper now.
I'll ask you. Yeah, I'll ask you about that. Yeah, that's interesting.
Ben, what with associated grade with respect to which filtration?
You put a degree on the generators where a merge of K and L has degree K times L. It's pretty easy.
So are you using GL and Spider? Are you doing GL and Spider?
Yeah.
But so you have a sort of some very special multiplication with diagrams that only picks up the top term. And that's easy to compute.
Yeah. It also describes the Demerzel operators on homology. So.
Is this like a J-ring version of the SL and Spider or something?
Not really.
By taking minimal, no?
Can I ask more questions about quasi-termination?
Yeah, sure.
So like, what do you need? I still don't understand. Like, so you have a loop. Like, what do you need to show to make it be confluent? Like, obviously you could have A, so, okay, you could have A is equal to B and B is equal to 2A, and this will not be confluent, right? Like, this is gonna be a problem.
Quasi-termination.
How do you rule this out? Like, what?
I mean, you have some cases when you don't need quasi-termination, but you only need quasi-normalization, which is you in any path you will be able to find an element on which you can only apply cycles or zero, and this can be enough. And otherwise, yeah. So it was a big part to show that when you know that you are quasi-terminating, like you have only cycles, to check the confluence also amounts to check the confluence of critical branchings in some way.
So I might understand that it just doesn't count as a loop unless it really comes back to itself with coefficient 1. Like, then you count it as a loop. It doesn't have to do with the shape of the pictures or anything. Just, once you have a loop, so if you can show that all cycles do eventually loop on each other, and if you can show all the other critical branchings, then you're done. Is that the statement?
And all cycles, sorry, can you say it again?
So if you can show all critical branchings are fine,
yeah,
and that the only non-termination is you eventually get into a cycle, then that's enough to show term.
Yeah, exactly. Yeah, exactly. Because if you have an overlapping between the rule that can create a cycle and another relation, it's already handled by the critical branching anyway. So what happens is that you have cycles that can arise, but most of them you can go out of these cycles and you reach the normal cycles and you forget about the cycles.
Okay, thanks very much. Let's thank Benjamin again.
Thank you.
And I'll stop the recording.